Hi, we present our work towards fast and scalable normal integration using continuous components. We study surface normal integration, which deals with reconstructing a depth map from an input normal map given camera intrinsics. Let's quickly revisit some of the main elements of this problem. As the name suggests, recovering depth from surface normals is essentially an integration problem, and as such, it is in general up to constants. Consider for instance the example on the left side. The chair and the wall can be separately reconstructed. However, the exact distance of the chair from the wall, that is the depth discontinuity, cannot be estimated since infinitely many solutions exist. In order to determine the correct scale, in object-level benchmarks, the typical assumption is that for any two neighboring points separated by a discontinuity, there exists a path connecting them along a continuous surface. Normal integration methods then typically exploit this implicitly by defining for each pair of neighboring pixels A and B a model of continuity, which describes the relation between normals and depth where the surface is continuous, as well as a model of discontinuity, which weighs equations based on how discontinuous the surface is considered. The leading model of discontinuity is the bilateral weighting scheme of Bini, which assumes that surfaces are semi-smooth. The equations and weights for all pairs of neighboring pixels are then aggregated into a system of linear equations where the unknown is a vector z tilde of logarithmic depth values, which is typically estimated using iterative least squares optimization. One problem with these approaches is that they perform optimization globally, that is, they estimate the log depth at all pixels at once. Additionally, they require many iterations in order to recover discontinuities. As a result, for typical object-centric maps from benchmarks, here shown on the left, their runtime is in the order of seconds, but for normal maps with more valid pixels, even at the same resolution, their runtime is in the order of several minutes, as shown on the right. In this paper, we focus on the question, how can we improve the scalability and runtime of these methods? To address this question, we observe that surfaces typically consist of large continuous patches, such as the body of the cat shown here, its head, leg, and ears. If these patches are separately reconstructed, retrieving the global surface reduces to estimating the relative depth scale of each component so that they are globally aligned. This reformulation has the advantage of using fewer variables, namely a single scale for each component as opposed to a depth value for each pixel. It also has fewer constraints, which are only defined at pixels on the boundaries between components. And finally, each component is typically much smaller than the full surface, which means it can be retrieved with a smaller optimization problem. Since components are continuous, per component optimization also requires fewer iterations because it does not need to retrieve discontinuities. More concretely, given the input normal map, we compute 2D components by considering the angle between normal vectors at each pair of neighboring pixels. If this angle is smaller than a chosen threshold theta c, we assign pixels to the same component. Initially, each component is reconstructed as flat. In the first step, we then separately reconstruct each component using independent optimization problems. We then optimize their relative scales, initially to globally align them, and later taking discontinuities into account. Optionally, neighboring components that share continuous edges can be merged over time. This further reduces the number of variables and constraints, which is beneficial for large input maps. Our method achieves state-of-the-art results on the standard object-centric benchmark dirigent in as little as few seconds. We show here some example outputs on scene-level normal maps, where the advantages of our approach are even more evident. The crucial aspect is that our method achieves runtime 1 order of magnitude smaller than log-depth pixel-level methods. Additionally, looking at the reconstruction, we note that by modeling large continuous surfaces as components, our method prevents the formation of spurious discontinuities, which are instead introduced by log-depth pixel-level approaches. Another example of which is shown here. Thanks for watching. Please check out our paper and code for more details.